a lot of the mathematics about what could happen, our predictive ability, even when we draw from a data set, is based on what we know about randomness or about what might happen. And the easiest, most theoretically driven version of this is probability. A random experiment is any process I do where the outcome is not predetermined, but there are a set of possible outcomes. This set of possible outcomes is called the sample space. And is usually referred to as S. S can be a discrete numerical set, a continuous set, depending on the experiment. How long is the last phone call you received? Well, that would be a continuous range because we can go minutes, seconds, fractions of a second. We could measure this, let's move on. Your current GPA. Again, I don't know that, but if I picked a student and asked what the GPA was, there's a set of results now depending on how many decimal places we round to, continuous or discrete. Number of customers in a line, result of throwing a die, result of picking a card. All of these are possible sample spaces. An event is a subset of our sample space. A simple event contains one and only one outcome. So I could say pick a card, any card, and one of those cards, queen of clubs, right? So I could say, that's my event. You pick the queen of clubs. Most of the time, we will indicate an event with some index on it, depending on how many I have. If I have a discrete set, even if it's a huge set, I'll number them from 1 to whatever. And so my sample space can be thought of as the collection of all of those individual outcomes, simple events, if it's discrete. On the other hand, if I was measuring the time you spent on hold on a phone call, that would be continuous, right? It would start at 0 and then just go up. You could have been answered right away, or you could be on hold for 37 minutes and change. That would be an interval as opposed to a discrete set like this. For the moment, we're going to focus on discrete spaces. Leo, you had a question?
I was wondering, like, is this like discrete, like, since they're only whole numbers, or they're like...
At this point, we're looking at discrete spaces. So if I think about pick a card, standard deck of cards, how many options are there?
52.
So it would be E1 through E52, right? For a standard deck of cards. And I could simply pick one of them for each number. the order that they appear in isn't relevant. But there are lots of different options. These events are equally likely. We presume. Now, we're going to have to talk about exactly what that means as we go forward. But if we consider something like rolling a die, then a standard six-sided die has the options 1, 2, 3, 4, 5, 6. That's my sample space. The assumption is that this die is unweighted. There's no force or special behavior that's going to make one of those numbers come up more than another. As a matter of fact, if you go to a casino that has a dice game, they will take the die by the corners, two opposite corners, and spin it. And if it wobbles, then it's started to become unbalanced, and they'll throw it out. One of the easiest ways to rig a die is to, if it's got, instead of actually having numbers on it, if it's got dots on it, is to drill those dots a little deeper or a little shallower. And that causes the die to be off center and off balance. I'm assuming we have a fair idea. In the same way, I could talk about flipping a coin. Assuming the coin is fair, then my sample space is heads and tails. Two distinct options for my coin. And the same chance of each option happening is what I'm looking for. But not all events are equally likely. Yes, sir.
When we use the word event, do we mean like rolling the die?
Yeah, no. The event is one of the outcomes.
Right.
A simple event is one of the outcomes. So this case, the event is I've flipped the coin. That's the experiment. Do you know if this coin came up heads or tails? Now I do, right?
Yeah.
But until that moment, could have been heads, could have been tails, and it was equally likely to have been either one. I roll the die, could be anything from 1 to 6. I pick a card, it could be any of the 52 values. A fair, equally likely, simple event. But the key word there is actually simple as opposed to event. Because I could ask you about more complicated events. Remember, I said an event is a subset. So I could think of a whole collection of things. Here's a new experiment. Roll 2 standard 6-sided dice. Now add the numbers together. Well, in one case, I could think of my events as the total is 2, the total is 3, the total is 4, the total is 5, right? All the way up to the total is 12. How many different ways can you roll a 12 on 2 standard dice?
Only one way, only 6 and 6.
But there are lots of different ways to roll a total of 7, aren't there?
6 and 1, 2 and 5.
I don't need them all at the moment, but there are more. They're not equally likely. So that's a bad description of my sample space. But those are compound events. One of the things we need to do to be able to find the chances of something happening is to know whether our event is compound or simple. And if it's compound, to know what simple events go into it. If I pick a student at Seton Hill, I can ask, what school is your major in? Everybody's got a major. What's your major? What school is it? There are 5 schools at Seton Hill. We have the School of Business and Technology, the School of Applied Social Sciences and Education, the School of Natural and Health Sciences, the School of Visual and Performing Arts, Business and Technology and Sciences, and the School of Humanities. These are not equally likely events. Why?
Students in each school.
There are not the same amount of students in each school. So I could say, hey, there are more students in natural and health sciences than there are in humanities. This is more likely to be chosen than this. I could go through and count how many are in each group. And then I'd have some basis for determining what's going on here. I can say the same thing about what year a student is. A traditional undergraduate student is either a freshman, a sophomore, a junior, or a senior. I can't use S twice, so senior gets an R. But again, those are not equally likely. Why not?
It's like the different types of classes, there's a different long number in each.
There are almost always fewer sophomores than there are freshmen. Almost always. People don't stay. They transfer out. They decide they didn't want to be at Seton Hill. They stayed for a semester, decided college wasn't for them, and got a job. Whatever it is, attrition occurs. Same thing from sophomore to junior year, junior to senior year. So these aren't equally likely. Quite frequently, I will be asked to list a sample space. My goal is to list it so that the things in it are simple events and are equally likely, if I can. But as we can see, we can't always. Questions? The probability of an event is the relative likelihood of an event within a sample space. The emphasis here is on the word relative. I will write P of E for the probability of event E. It doesn't matter whether E is simple or compound, as long as I can figure out its relative likelihood. I can guarantee something though. Matter of fact, I guarantee a couple. If I have any event probability of E is always bigger than or equal to 0. If it's equal to 0, that thing can never happen. But it's also less than or equal to 1. And if the probability of an event is 1, then it is certain to happen. It must happen. But no matter what the event is, whatever we figure out for a probability, the number should be between 0 and 1. So if you're doing a calculation and you get the probability of this thing is 3.7, something not up. We described our sample spaces as a bunch of events, right? So if I think of my sample space as a bunch of simple events, or even as a bunch of compound events, but that list has no overlap in it. We'll discuss what that means in a little more detail in just a minute. Then, the probability of each of those things added together has to be 1. I'm going to do my experiment. Something's going to happen. That should be I equals 1 to 1, 1 to n there. That dot didn't get separated enough. There we go. So if I think, what's the chance? Rolling a die. I roll a die. I could roll a 1, I could roll a 2, I could roll a 3, I could roll a 4, a 5, a 6. That's all that could happen. If I add up all the probabilities, that has to add up to 1. I flip my coin. We said there were 2 outcomes. Total probability of landing heads plus the probability of landing tails has to be 1. My choice of students and what school they're in, or what year they're in, the chance of a freshman plus the chance of a sophomore, chance of a junior, chance of a senior, has to add up to 1 every time. Because something is going to happen when I ask a student, are you an undergraduate? Yes. What year are you in? I have to give an answer. And since those were the only 4 answers that were allowed, those are the 4 choices I have. Total has to be 1. Question. Yes.
How can it be PE minus equal 0 and also equal 1?
Okay. So it's the number we come up with for our probability can never be a negative number. So it's got to be the worst, the lowest it can get is 0. I want you to flip this coin. When you flip this coin, tell me what is the chance that when you flip the coin and it lands on this table, that it will stay balanced on edge perfectly?
Might be like a very.
It's going to bounce and it's going to fall over, right? That's a chance of 0. But if I throw this coin in the air, what's the chance it's going to hit the carpet? It's always going to hit the carpet 100% of the time, right?
So it can be both equal 0 and equal 1.
Not at the same time.
Oh.
Each number can be no smaller than 0 and no bigger than 1. Those are like fences. You have to be between here and here. So now the question is, if I have some event, how do I figure out its probabilities? There are several different ways to do this that are distinct from one another methodologically. I can run the experiment a whole lot. I could ask you to take this coin and flip it 100 times. And take the relative frequency of heads and the relative frequency of tails and say that's the probability of heads and that's the probability of tails based on your 100 flips. Or maybe I have you do more, 1,000 flips, right? The more I do, the more sure I'll be of my results. The word empirical means from experiment. And I'm really just using my relative frequency out of my histogram. That's option one. Option two is classical or theoretical probability. Where I go through the process itself and I know the probabilities before I do anything. This is a mathy version. We have to make some assumptions about the outcomes and we have to do a whole bunch of counting. The third method, typically called subjective probability, is an informed judgment. This is an expert opinion. Okay. Chance Steelers going to win the 2027 Super Bowl. I haven't the foggiest idea. I don't follow football that closely, but somebody who does would be able to come up with a subjective opinion about what they think is the probability. I am the absolute worst person to ask a sports question to about then trying to make a real definition. This is, by the way, one of the biggest pieces of modern data analysis is training your model to become that well-informed expert. Page 156 has our three views of probability in a little table here, giving us these definitions. Questions? Yes.
For theoretical, it's like we're assuming that we already got the data
I have not done the experiment. I don't have any data. I'm gonna look at the way the experiment happens.
What would be an example?
I got plenty of it. Pick a card. Assumption. The cards are in a random order, and all 52 of them are different. I got this back from Dr. Burns, so I'm assuming that's true. But if I said, come pick a card, what's the chance you get the ace of spades? There's only one ace of spades in this whole deck, right? And there are 52 cards here. So if the cards are equally likely to be chosen, then my chances should be 1 out of 52. Completely theoretical. Have you picked a card yet?
No.
But I have a chance in my head that I already know of the way that could occur. Let's write that down formally. So if I have A, our set of an event, this could be a compound event, it could be a simple event. So I'm going to define the size of A. These vertical bars are usually read as the cardinality of A or the size of the set. Number of simple events in A. Now, Jacob, in your question, the event I gave was ace of spades, one option, right?
Yeah.
But I could say, what's the chance of picking any ace? In which case, there are now 4 options, right? What's the chance of picking any heart? Well, there are 13 hearts in the deck. So I can use that number as simple events. I'm going to say I'll have the same thing for S. And then the theoretical probability of event A just divides. Again, I am assuming all simple events are equally likely. These calculations are done in advance. I don't actually have to do the experiment. I just have to know about the experiment. Now, the problem is that S could have a really large number of things in it. And A could have a really large number of things. They're based on pure logic, theory, not always possible in business situations. I might not have complete knowledge of all the samples space, or I might not have complete knowledge of how likely each individual event is. But assuming a fair coin, I flip this coin, what's the chance that came up heads? 50%, right? 1 out of 2 options. 1 in my event, 2 in my sample space. If I'm looking at not just 1 card, but 2 cards, you're going to get 2 cards from this deck. Well, then I have to figure out how many ways can you get 2 cards. And then I have to figure out how many possible collection of 2 card sets are there. Counting these numbers may be non-trivial. There's a lot different ways to get 2 cards. There's even more if I tell you the order in which those cards are given to you matters. This is the exact reverse of theory. Theory says of empirical. Do the experiment a whole bunch of times and tell me what you see. In which case, when I do empirical, I'm going to let F be the number of times A occurred. N is the number of times I ran the experiment. This then would tell me that the probability of A is F over N. Again, here's a coin. You said the chance came up heads was 50%. Go flip the coin 1,000 times. Yeah, I got better things to do with my life, right? But somebody somewhere out there is actually going to flip this coin 1,000 times. I will probably take a little mechanically fireable piston, and I will put the coin on top of the piston, and the piston will be just off the center of the coin, and I'll fire the piston, it'll flip the coin in the air, and I'll watch it land. I'll just let this happen 1,000 times. I won't have to do it. I'll have a camera on it, and it'll count heads versus tails. There, I flipped the coin 1,000 times. By the way, that was actually done. I flip a coin. You watch it spin in the air. But I can flip that coin so it spins very fast. Or I can flip that coin so it spins very slow. Piston will flip it the same way every time. If I put that coin heads up, the speed of the piston will tell me how fast it rotates. I can rig a coin if I learn to flip at the same speed every time. You want to talk about sleight of hand? I flip the coin so it comes up tails every time. Just like I can force a card out of a deck. I'm not that good a magician. Not going to be me. But it can be done. Please note, there's this rule called the law of large numbers. And the law of large numbers says that as you do the experiment more and more and more and more and more, these two results get closer and closer together. So I may flip this coin 1,000 times and end up with 503 heads and 497 tails. That's not 50%, that's 50.3%. I flip it another 1,000 times. So I've done it 2,000 times, and I end up with 1,004 heads and 996 tails. When I'll probably have heads, it's 50.2. If I keep flipping, I will close in, getting closer and closer to 50%. From a calculus perspective, we would say a limit is occurring, and the limit of your empirical probability is your theoretical probability. the extreme version of this is to say, hey, this coin flips heads 0% of the time, because I flipped it once and I got tails. Isn't that stupid? That's the fewest possible experiment I can do. And so I'm going to be far away from my actual theoretical probability. There are some challenges to empirical probability. Time and money. I've got to spend the time to flip this coin 2,000 times. Or I've got to build my little coin flipping robot. That's expensive. Every repetition must be exactly the same. So I can't suddenly decide that instead of flipping it, I'm going to spin the coin and see which way it lands. That's a different experiment. And by the way, that one, the odds are not 50-50. Especially on pennies or nickels. What's special about a penny or a nickel? Anybody have a nickel? Nobody carries cash anymore. I know, I'm a weirdo. What's special about a nickel? A dime and a quarter have ridges around the edge. A nickel and a penny are smooth. By the way, this dollar coin technically has words printed around the edge, so it also has a marked edge. What does having a smooth edge do to the coin? Anybody know how a coin is made? How do you make a coin?
It's like pressed like in some kind of magnetic press down.
But before it's pressed down,
It has to be shaped first.
and that means I have to cut it out of a sheet of metal. If I take a cutter with a smooth edge and I cut straight down and pull straight up, you know what happens to my coin? It stays stuck in the tube. So if I want the coin to fall out, I have to tip the edges of the cutter so that one edge is different than the other. And it has to be out so the coin will fall out rather than in. The coin will get stuck this way, right? That means that the edge of a nickel isn't flat. It's tipped. Then I put the face and the tail on it, the head and the tail. Well, if it's tipped, then one of those is more likely, when I stand it on edge, to fall than the other because of the angle of the side of the coin. Spinning a coin is not 50-50, whereas flipping a coin is. By the way, it's like 49.6 to 50.4. It's really close. But I actually saw the experiment. They took 10,000 new coins, balanced them on edge with the same orientation on the same table, and then went and watched them all fall over and counted. I think they did that 200 times. That's a lot of coins, isn't it? Is the process stable over time? So that process that I just described will eventually not be rigged, because over time, the coin's edge will wear flat. So that coin may become fair the longer it's used. We might have outside factors and laws that prevent us from doing data collection certain ways. Think of the flu vaccine or the COVID vaccine. When the FDA rushed through the COVID vaccine, they shortcut a lot of the trials. So they didn't do them. Secretary Robert F. Kennedy wants to change that and require all of these trials, which means a longer lead time to get a vaccine out to people. That changes whether or not we can do the empirical versus the theoretical. What if the event's not repeatable? I'm never going to get the same two teams to play the same game twice. I don't care if you've the basketball team. I don't care if you faced Clarion last week. You have a different week, different people feeling differently, people who are injured or not, people who are on hot streaks or not. They're different teams. The event's not repeatable. So whether or not I can actually do the experiment the same way over and over and over, I don't know. On the other hand, somebody who's been keeping statistics or analyzing basketball teams for the past 3 years might be able to tell me one way or the other who's got the edge in the next basketball game, Clarion or Seton Hill. Somebody might be able to say, based on these factors, we now know something. That's subjective probability. It requires a minimal knowledge and understanding of the experiment, of the idea, and of the event. Questions? Some events can be modeled. And if I can model an event, then I might be able to run the model a lot. I can put something on my computer. Flipping a coin can be turned into a computer program. So I can flip a coin 150,000 times by letting my computer go, and it's done. But again, that's assuming I've made a model correctly. Since I know that in the long run, empirical probability closes in on theoretical probability, I should come up with rules and calculations that I can do for theoretical probability, and then I can use those in advance to place some knowledge into my own head. So let's think about an event A in a sample space S. A is a subset, right? So based on ideas about sets, some of you may have done some classes that involved sets before. Some of you may not have. Those of you in the discrete math course, we're going to do that in the next couple of weeks. But the ideas here are fairly general. I have this sample space S. That's the universe of all the things that could happen. I'm going to represent that by a big box. And then my set A is somewhere inside this. What's the name of that sort of picture?
There's like a subset, there's like a subset.
But there's a name for a picture involving sets like this. It's named after the guy who came up with it. It's called a Venn diagram. Be a bad joke because I don't always make pictures of sets, but Venn I do. Okay, wait a minute. I have all of this additional space outside of the set A. All of this stuff out here. The part of S that's outside of A is going to be called the complement of A. Now, different books denote this differently. Some books call it A prime. Some books call it A with a bar over it. Some books call it A with a little C as a superscript. So A complement, all of those things. Sometimes we call it S take away A. All of S take away all of A. Well, let's think about probabilities for a moment. I do the experiment in this sample space with this event. What is the chance that I end up in A complement? Hold that thought, Leo. Leo's in the other class, sorry. There are only two choices, right? Either end up in A or end up outside of A.
Minus the probability of A.
Because the whole thing has to add up to 1. Or I could write it that way. I could write, hey, the chance of A complement and the chance of A must be 1. So if you move this to the other side, you get this version. Oh, I like that. A or not A. It's almost Shakespeare. Huh. All I needed was the Venn diagram? I like this. Yes, Leo, question.
Would it be less than a 0.5% chance? It looks like a small, minor thing.
I have no idea what the actual ratio of these areas is, but yes, in this case, I think A is less than half of the area. So yes, this would be smaller than a half.
I'd say about 30% maybe.
I think that's fine. Could be anything. But if that's 30, then the outside is,
70.
and there you go. Because they have to add up to 100%. Okay. I have more than one descriptor for any card in the deck. Yes? I have suit, I have color, I have value for each card. So if I have a deck of cards, $52 cards in the deck, half of them are red cards. Half of them are black cards. Red cards are hearts and diamonds, black cards are clubs and spades. There are one of each value in each suit. Aces, 2, 3, 4, 5, 6, 7, 8, 9, 10, jacks, queens, and kings. From a theoretical calculation, chance of red.
Maybe a 50% chance.
What's the chance of a queen? Which simplifies to 1 out of 13. If you want to use decimals for these, that's fine. I don't, because I think the decimals for 1 over 13 is ugly. I'm just going to leave it as a fraction. I will answer the following question next time. What is the chance of red and queen? And the reason I will answer that next time, because I've run up against the clock for today. So I will see you all on Wednesday. Have a wonderful rest of your day.